Okay, so now first let's talk about trying to do some review for chapter 2 quiz, okay, which is scheduled on March 25th, so that's it's just coming Thursday, okay. Okay, so first let's look at the, um, the homework list, okay. So what you need to do is you want to review this homework set, okay, and from number 2, the second problem, up to the problem number 8, okay. So I'm going to guide you through how you are going to review it, and probably you have done review by yourself, okay. So I'm going to circle these important problems, okay, important problem. Now, how do I rank them? Now, first one, so in the test, you will have a similar problem like this, okay. So I can tell you what exactly the problem is. So one thing for sure, so the number 2 problem, the problem will be different, okay, slightly different, right? But actually, this has to be handled in a similar way. I mean, as we handle the homework problem, or the examples in the notes. Okay, so that's the one you have to prepare. And the next one is a very important one. Is you want to be able to prove the combination of limits. So you are not supposed to use the result. You should start from the definition of limits to prove this. So that's what I'm saying is you're using epsilon argument. That means you from the basic, okay, from the basic definition you prove it. Now here, this is the problem we have. Actually, we went through and during the lecture, but we also went through an important example like this. You talk about the square, I mean xn squared. So there's a square involved, or basically there's a product involved. Okay, so this is a very nice problem. So xn squared plus 2xn, what goes to x squared plus 2x. So, I mean, combine two different set of technique, and we know how to do that, right? So, so this is something you need to prepare also. Okay, not just the linear case. Okay, so that's number 3. Number 4. Number 4 is a very typical problem. I'm going to talk about this later. Okay, in a minute. So this is a typical problems, and you have to be very careful with this one. Prepare for it. But well, there's a different kind of situation. Here, the limit equal to, you want to show that eventually the xn is greater than 0.99, right? Okay, so the important thing is to you learn the skill in the pros, the method approach. Okay, you should be able to use the same approach to prove a similar problems. Okay, for instance, just thinking about the limit xn equals 1, this case. Now here, you're required to show that xn is greater than 0.99 for n large enough. Now for the same argument, you can show that actually the xn should be less than 1.01, 1.01, right? On the other side, you can prove this, just so you can practice on that. So number 4 is a typical problem. And number 5, I circle by green. Okay, it means that you first, well, these number 5, number 6, and number 4, they're all related, the same kind of problems. So my recommendation is you first fully understand number 4, and then you spend time on number 5 and number 6 in this order. But it doesn't say that these are number 5, number 6 is not important. One thing is in the right order of reviewing, you should review number 4 first, then number 5, number 6. Okay. Then, of course, there's a number 7, and number 7 is also, I mean, it's also you can review it. Also circle in red. Also, okay. So we have done a full proof on this already, so I don't see the problems. And number 8. Oh, okay. So the circle. Sorry, there seems to me there's small mistake. So I forgot to circle number 8. So number 8 is extremely important. So there must be a problem like this in the test, like number 8, okay? So I'm giving you a sequence, like I tell you the first term, then I tell you the other term using a formula, just like this. And you need to show that, okay, maybe the sequence is or you may use induction to show that the sequence is a increasing sequence and bounded, and then the sequence must carry a limit, and then you can take a limit on both sides, you find the limit, right? So it's a very typical problem. So there will be a problem. I can tell you there will be a problem like this in the test, okay? Now, besides this, so you can also, there will be also a problem like involving Cauchy sequence. Okay, so this means that I'll give you a sequence. I want you to prove that the sequence is a Cauchy sequence. Okay, and we have 3 examples in the lecture. So they are all, so you can, the problem that appear in the quiz will be similar. Okay, so I'll give you an example like this. If you take xn, so this is a example we studied in the lecture. Okay, so we show that this xn is a Cauchy sequence. All right. So so this is the basic idea of what kind of problem will appear in the test, especially those circled by red. But I forgot to circle 8 by red. Okay, so this is important. Don't forget number 8. Okay, so this is the list of problems. Okay, then I'm going through each problems. Okay, for some problem, I just I'm putting all these slides together. All these slides together, so it's easy for you to review, to view this video again, to review them, okay? Like, so I'm not going to say anything about number 2. Number 2 is very typical. You look at, I don't see there will be a problem there. Hold on just a second. There's any questions? Okay, yeah. So I'm going to comment on number 3, number 4, and so on. So some of the problem I'm going to go through with you. Okay. So the first is number. Okay, this is the example problem. It's not in the homework problem. I just mentioned example problem. So you can see there's a square involved. So this means that this proof should relate the product case and the linear case. Okay. So this is the full proof we went through during the lecture. So you can review this proof, okay? As you have to get an idea how do you handle a similar case like this, okay? And so you just review it by itself, okay? Then I want to say something about this number 4. Number 4 that shows that if limit equal 1, so xn is greater than 0.99, okay? So the idea is you choose, because you have a sequence which carry a limit equal 1, okay? So you can choose epsilon equals to 0.01. Because for any given epsilon, we can plug in this epsilon into the definition. You have an estimate, right? So I choose a particular epsilon. Okay, that's a difference basically. That epsilon is the difference between limit and the 0.99, right? So you look at a picture here. So I'm going to use this epsilon and create a neighborhood from 0.99 to 1.01, this neighborhood of 1, the neighborhood of the limit. So you can see as n large enough, okay, so that means there is a k, where n greater than k, the xn will be inside this neighborhood. Now, as long as xn is inside this neighborhood, you can see that xn must be greater than 0.99. So that's the basic idea. So when you write a proof, you have to use epsilon argument to write these steps, each steps clearly, okay? So the first thing is you can say that you choose epsilon equal to 0.01, then because the limit exists, which is equal 1, So this means that there is a k such that when n greater than k, okay, then the distance between xn to the limit, that's xn minus 1 absolute value, is less than 0.01. So this is once you choose epsilon equals 0.01, so you got all these things because we know the limit exists. 1 is the limit. Now, then you handle this inequality. This inequality carries absolute value sign. The key step is to remove this absolute value sign. Okay, you get this. So that means xn minus 1 is greater than minus 0.01 and less than 0.01. So basically, once you remove the inequality sign, you got two inequalities, left side and the right side. Okay, so for our purpose, we want to control xn from below. So we use the left inequality. How do you use left inequality? You just, from this original inequality, you just add 1 to each side. Okay, or you can just concentrate on the left inequality. That's minus 0.1 less than xn minus 1. Then you add 1 on both sides. You'll get, on the left side, you become 1 minus 0.01, which is precisely 0.99, less than xn. You immediately get the result. Okay. Now, if I want you to prove that xn is less, I want to control on the other side. I want to show xn is eventually less than 1.01. Then you use the right side inequality. That means xn minus 1 less than 0.01. Then you add 1 on both sides, you will get what you want. Okay, so that's the basic technique involved in this probe, right? So what you need to know is, this this idea, the way how to prove this can be applied to the other case. Okay. Okay, number 5. Number 5 is the, I just include the whole page here. Okay, so you have to use, so as you have a non-negative sequence, a positive sequence, you want to show that the limit is also non-negative. So basically this involves the inequality, okay, inequality. And here there's a full proof, it's written here, okay. Again, you can see that the key is that you have to find a way to remove the absolute value sign. And so this is what then you can handle this in this way. So that's number 5. Okay, and number 6, I just mentioned a few points. The number 6, I mean, when we handle the combination of limit in the division case, okay, and but in this case, this is much easier than division case because square root xn can be removed. So you can see the absolute value between square root xn minus square root x is eventually controlled by absolute value xn minus x divided by square root x. So therefore, as long as xn minus x is less than square root times epsilon, then square root will cancel. So you get epsilon. Okay, so this is a very simple way. I mean, it's also very simple to handle this. Okay, so that's number. Then we come to number 8. Number 8 is an important example. And this homework, we have talked about this already. So in this case, you can see that the sequence is defined by this formula. And what you need to do is actually you want to actually, first you have to prove that the sequence is the increasing sequence and the bounded sequence, okay, and hold on just a second, all right, just a second. Okay. All right. Okay, sorry about it. There's a meeting announcement. Okay, so you have to be able to handle the similar sequence like this, but the method is unique. You show that the sequence is bounded, and it's a bounded, and either increase or decrease, doesn't matter. Normally, for all the example we associate, we're dealing with increasing sequence, okay? And if it's happened, it turns out to be a decreasing sequence, then the same thing works, okay? But because the monotonic criterion apply to both case, increasing and decreasing case. So the first thing is you use induction to prove the sequence is a monotonic sequence. For instance, it's an increasing sequence, and also show it is bounded sequence. And then you can pass on limit on both sides. You get the equation. Normally you get the equations. And then solve this equation, you can find the limits. Okay, so that's number 8. And finally, I mentioned that there is a problem with the Cauchy sequence. So this is a good example. But I'm not saying that this example will appear in the test. So tests will be different from this example, but in a similar fashion. Okay. I'm not going to just change 2 to 3. I'm telling you the truth. Okay, I'm not changing 2 to 3, but it's very similar. So you have to. So the key is you estimate the xn minus xm. Okay. So you can see this. All these terms are actually a part of the geometric sequence. Okay, and the geometric sequence is computable. So therefore, you can show that everything, you can control everything so that it's less than epsilon. Now, if you have a different sequence, you have to find way to control the difference. Okay, control difference. Yeah, so that's it. So that's all the things I need to tell you about the quiz. Okay. Any questions? If no questions, then we need to begin with the new chapter, the chapter 3. Okay, so I'm going to stop sharing this one. So there's some questions. All right, okay, never mind. So we're going to begin talk about the chapter 3. Hold on just a second. Okay, very good. So now we are begin with we are now study chapter 3. Okay, and remember in this class we have 5 chapters. Okay, chapter 3 now, and so you see our position. We have finished chapter 1, chapter 2, chapter 3. Chapter 3 is topology of Rn. The Rn is n-dimensional Euclidean space. Now, good picture about wow. When n is greater than 3, you cannot imagine such a space, right? It's an abstract space. So what you really want to think about is treating the Rn to be R2 or R3, something like this, okay? Okay, so what we are trying to do here first is to define certain spatial sets in R. So in this class, because n normally consider n is normally reserved for the index, okay? And so that's why dimension sometimes is called P. So we consider the piece dimensional Euclidean space. So we're going to talk about open sets and the closed sets. And these are important sets in the Euclidean space, okay? Like in the one-dimensional case, you can think about open interval, okay? Open interval is a very special open set. And closed interval is considered the closed set, okay? But in the general case, open sets and closed sets are more complicated than just intervals, okay? So that's what I'm trying to study here. So let's get familiar with those Euclidean space. So because we are now talking about multidimensional space, RP, so therefore the points. So we're not talking about number anymore. we talk about the points. So point carry coordinates. So there's a p-dimensional Euclidean space. So therefore, each point carries p components, p coordinates, x1, x2, xp. Okay, so this is something you're familiar with. You learned this maybe from calculus. Okay, so in order to define open set, and we need to define open ball first. So given a point x, and then you choose a positive number that's called r greater than 0. Okay, now we denote the brx. Brx is what we call open ball, and the center at x, and with radius r. Okay, so this means that this open ball is defined to be the collection of all the points denoted by y, such that the distance between x and y, and the distance from the center, is less than r. So think about two-dimensional case. It's an open circle. It's just like that. This is an open circle. Now, if it's three-dimensional case, it's just open ball. So when I say open here, you can see the boundary. The boundary are denoted by those broken line, broken curve. So this means that the boundary are not included in the set Brx. Actually, you can see that the inequality is strictly less than inequality, strictly less than r. No equal sign attached. So that's why it's open ball. Okay. Now here we use the distance. We talk about distance between x and y. So this means the distance is defined to be Euclidean distance. So that means you make a subtraction on each components. Then you compute the sum of squares, and you take a square root. This is called Euclidean, the standard Euclidean distance between the points x and y. So every time we see the distance here, okay, so this means it's defined in this way. And this is not an absolute value because we're talking about points. Okay, not absolute value. All right. So this is the Euclidean distance between x and y. Now, and then the next thing we want to talk about is what we call is a neighborhood of a point x. Now, this concept is, in some sense, it's not necessary, but however, we're still involved here. I just introduced what we mean by neighborhood of x. Okay. Okay. So here from the picture, you can see there is a point. So the point is considered is x point in RP. Okay. And then there's a set called U. U include, I mean, the point is actually this set contains the point x, right? Okay. Now, what I mean by this U is considered a neighborhood of this point. What does it mean? So the concept is very simple here. It means that U is a neighborhood. It means that there is a ball, Brx. The whole ball is contained in U. Okay, so that's the case. So if there is a ball centered at X, which is contained in U, then this U is a neighborhood of X. So that's a simple concept. Okay, this is what we mean by neighborhood. Okay. Okay. We know that the one thing we know from here is that the ball itself, Brx itself, is a neighborhood of X. Okay, because you can just take the ball itself to be, I mean, the ball itself is containing the ball, right? So therefore, it satisfies the definition. So any open ball is a neighborhood of X. Okay. All right. So this is a few simple concepts. Now let's think about how we define the open set. What I mean by a set is open. Basically, open set means that there's no boundary. All the boundary points are removed, are not involved. Okay, then the set is considered as open set. It's open. Okay. Now here's a definition. Okay, let's consider set G in RP. Now this set G is said to be open in RP. It means the following. It means for every point in G, for every point, okay, there is a ball centered at X, which is contained in G. So in other words, this means that the G is a neighborhood. G is a neighborhood for every point in G. Okay. So I can show a picture again. So you can see that the G here, you can see a blue set G is the set I talk about. Okay. So you can see all the boundary points are removed here. So you can see the interior point here. So those I'm choosing 2 points here inside. So you can see both points. So no matter which point you choose, here I choose 2 special points like this. You can see there is always a small ball surrounding this point, so that the ball itself is inside G. Okay, so in both cases, you can see you can find the ball, right? But for some point, if the point is very close to the boundary, then the ball is very, very small. Okay, so as soon as you can see that the points, no boundary point is involved, you can see this set is open set. Okay, but you cannot define open set by saying that a set without boundary point. You can't say that, okay, because you haven't defined exactly what is boundary point here. You can only define the open set through the definition here. I mean, for every point in G, there is a small ball surrounding X, so that the whole ball inside G. Okay. Now here actually another you have to pay attention that if the set G involves some boundary point on the boundary, so then the G cannot be open, because for that point, so for instance in this point, you can see the point is on the boundary, then this condition never satisfied, because you cannot find a ball so that the whole ball is inside G, because no matter how small the radius is, the ball surrounding this point will always touch the outside point, will never be inside. The whole ball will never be completely inside. So that's why for open set, no boundary point should be involved. Okay, so this is what I mean by the open set. Okay, so examples like open intervals. Open interval is open ball. So okay, see our interval is A to B. It's an open set. Okay, or you can see a ball. Ball is an open set. Ball is open set. Okay. So this is so the open set concept is very simple. Okay, so it can be defined through this kind of definition using the small ball to define this. Okay, now so that's the definition. But the more importantly, we need to talk about the open set properties. So that's important. Okay, so what means open set property? It means that suppose you have a number of open sets in front of you, and for those open set, you can do some set operation. For instance, you can put open set union open set, or open set intersect with another open set. Okay, so you can perform all different kind of operations. Now the question is, so after this operation, the new set, whether the new set will still be open set. So this theorem will tell us that. So this means that as long as the union and the intersection is concerned, and the resulting set will still be open set in some sense. Okay. Now, before we can see this, we first have to make some arrangement. So we know what we mean by empty set, right? Empty set. And so here we want to, now what I mean by empty set? Empty set, that means a set without any elements, okay? And we are going to define, we are going to consider the empty set to be an open set. Now there's no reason for that, okay? It's just, we can consider open set to be a special. We just consider the empty set to be a special open set. That's it. There's no other reason, okay? Another thing is you think about the whole space. The whole space RP, of course it's open, because every point in RP you can find ball completely in RP, right? So the whole space itself is open set. There's no problem. Okay, so when we talk about open set, then there's two trivial open set. One is empty set. The other one is the entire space. They are all open sets. Okay, now let's thinking about the non-trivial open set. Now here's the result. It says that the intersection of any finite collection of open set is open set. Okay, so that means you maybe you have a number of open set in the collection, and you take an intersection of that. You know what I mean by intersection, right? Intersection will be a much smaller set, but we're going to show that it's open. But here, there's a condition in saying that the it has to be finite. It has to be a finite collection. Okay, so this means that when you talk about open set intersection, okay, in order to for the resulting set still be open, normally you have to put this restriction. That means you talk about only a finite number. You are dealing with a finite number of open sets intersection. We're going to see the example. If the collection is infinite number of open sets involved, then the intersection, okay, the intersection may not be open anymore. So that's the part B. The part C is the union. Union means that for the union, there's no restriction. Okay, so that means union of any collection of open sets is open in RP. No question asked. Okay, so these three results is called the open set properties. Okay, hold on just a second. Okay. Sorry, there is an important message from the department. I have to answer immediately. All right. Okay. So now we're going to begin to prove it. Okay. For part A, so this is just a definition. There's nothing to talk about it. So we're trying to begin talk about part B and part C. All right. I'll talk about part B and part C, okay? Hold on just a second. Okay, I can't see the chart. Okay, never mind. Okay, so this is what we're trying to do. So let's prove the part B, okay? So let's thinking about you have n open sets. So just still what G1, G2 up to Gn. Okay, in the reality, so we cannot choose a picture of n open set. That will be too complicated. So what I'm trying to do is to consider two open sets, just G1, G2. And then from the picture, you can easily see the intersection, right? You can easily see the intersection. So we're going to show in this case, the intersection. So when going through a proof, I'm dealing with n open set. But in the picture, I only show two open sets. That to demonstrate the idea, okay? Okay, so we're trying to look at the collection. I mean, the intersection. We're going to show that the intersection is open. Now, how do you show the intersection is open? So you are going to show that for every point in the intersection, there's a small ball, which also in the intersection to complete the proof, right? So by the definition. So here we pick a point in the intersection, okay? Now, because we know all the set Gn, G1, G2 to Gn, they're open. So therefore, so now I can apply the open set concept, okay? So there is an RK and such that BRKX belongs to GK. So for each G, and you can have a ball, okay? A small ball surrounding X contained in the corresponding G. So you have a NG G set. So you have an N ball there. But in the picture, you can see that we are only dealing with two sets, two open sets, okay? So we have reduced to N equals to 2. Okay. All right. So what exactly mean by choosing this ball? So for a picture like this. So for the G1, so I know that this point is in G1. So there is a ball, okay? So BR1X. BR1X is in the G1. Okay, completely in G1. Now this ball may not be in the G2. Okay, you can see that actually some part of it may be outside of G2, right? Because we're just thinking about this point is a G1 point. So the ball is covered inside the G1. Cover this point may not contain G2. But you know that G2 is open set. So for G2, there is another ball surrounding the same point X, which is in G2. Okay, so this ball obviously is completely in G2, but maybe not in G1. Not completely in G1 for the same reason. Okay. So for two sets, suppose you have just G1, G2. So this is what happened. So when I pick a ball for each G, so you are going to have a picture like this. Okay. Now here in the Pro, I'm having N ball with radius R1, R2 to Rn. Okay. So now let's pick the minimum of all these radius. So there's a finite number of radius. Okay. So I think I should change the K to N. I pick the minimum of this radius because there's a finite number of positive number involved here. Okay. So you take a minimum of all these finite number of positive number. So therefore, the minimum self is greater than 0. Okay. So in the picture, it means that you're taking a minimum R1, R2. So I choose this ball. Okay. So BR. R is the minimum. So you can see this ball, it's a red ball. It contains in both previous ball. Okay. So this means in the Pro, this means that BRX will contain in each of these balls. So therefore, it will contain in all the G set. Okay. And so you can see that, so therefore, this ball must be, because it's containing all the open set GK. So therefore, the BRX must be in the intersection. So this means I found a ball centered at X, which is also in the intersection. So this is true for every X in the intersection. So therefore, this shows that the intersection of GK is open set. That's the Pro. Okay, so basically the Pro is basically applying these definitions, repeatedly applying this definition, and you can find the result. Okay, so here's an example. Example here, you have a open set. I mean, it's an open interval from -1 over n and 1 plus 1 over n. So sorry, I keep making mistake in the notes. Okay, the right side is supposed to be 0, 1. It's not A and B, 0, 1. Okay, you take all the intersection here. So you have infinite number open interval here. You take intersection of all these infinite number of open intervals. Then you finally come up with a closed. It's a closed interval from 0, 1. It's no longer open. It's no longer open. So this shows that the for these properties, and we must make a restriction on the number of open sets involved. Only when you have a finite number of open set, and you can be sure to say that the intersection is also open. Otherwise, the intersection may be not open. Okay, so this is the part B in these properties. Okay. Now part C is much simpler. Okay, much simpler. So in the part C, we're talking about union. Okay, union. Now for the union, you can have infinite union or finite union. It doesn't matter. It doesn't matter. It's not going to change anything. Okay, so here I'm using G alpha to be the family of open set. Now I'm not using Gn for a reason. B alpha, now here's something maybe we can talk about later. I mean, it's like countable and uncountable. You using G alpha meaning that this family of open set may be not countable. We'll talk about countable set later. Okay. Anyway, you have a family of open sets. This collection, okay, maybe involve infinite number of open sets. Okay, it doesn't matter. So here we're trying to talk about the union of all these open set. Okay, so what I'm trying to do is so I take an X in the union. So for the same reason, then I want to show that there is a ball of X also containing union to conclude that the union is open set. Okay, so I'll pick a point like this, and then you can see this point must contain in one of the G set. Maybe it belongs to G alpha naught for some alpha naught. Okay, so this means that this X has to be contained in one of the open set. Okay, and then you can see that because G alpha naught is open, so there is a R such that the BRX is contained. The notation, I have to fix the notation. The BRX is contained in G alpha naught. The whole ball is inside this open set. Okay. Now, once this is true, then you can see since the G alpha naught is contained in the union, so therefore this ball also contains the union, and this shows that the union itself is open set. Okay, so you can see the proof in the union case is much easier. It's almost straightforward. Okay, so as long as you have no matter how many open set you have, finite, infinite, and the union of the open set is always to be open set. Okay. Now another thing I want to continue here a little bit further is the definition closed set. Now closed set has a similar property as the open set. So I'm going to leave the closed set property later. We'll talk about this after next week after the quiz. Otherwise, I don't want to put too many things today here. So you have more time to review for the quiz, okay? Now we talk about definition of closed set. What exactly mean by closed set? So here's the definition. A set F, okay, is said to be closed if its complement, that means the whole space minus F, is open. So how do you see a set is open or is a closed or what? You look at the outside of the set. If the outside, the complement is open, then the F itself is a closed set. That's the definition. Okay. So in this case, you can see that so suppose you pick a point. So what I mean by outside is open. So this means for every point not in F, there is a ball for that point. The ball itself is completely outside. So it should happen like this. Okay. So if this happens, then you can see that the set is considered as a closed set. So if later when we dealing with some other problem, then we want to show that a set is a closed set. Now, how do we prove this? Normally, you have to argue the complements. You go ahead and try to show that the complement is open. Once you can show complement is open, then this will imply that the set is F. Some example like the interval, closed interval. Sorry, there's a mistake. There's a lot of things to correct. I mean, the closed interval is a closed set. Or the ball with equal sign involved. So previously, when we defined BRX, we did not use less than the inequality, strict inequality sign. But here, if I put the equal sign inside, that would be less than or equal to, then you can see the boundary is included in the ball. Then this is what we call a closed ball. And the closed ball is a closed set. Okay. So this is a definition of the closed set. Okay. And then we have the closed set property. I just mentioned this. And next time after the test, we're going to prove this. Okay. And so there's still also ABC. I can go through this after the test. All right. So this is all I have to say. Do you have any questions? Any questions?
Is it true that like all of RP would be an open set?
Yeah. Okay. RP is an open set, and also the RP. Sorry. So there's a typo. It's closed. So you can see the part A saying that the RP RP is a closed set. The empty set, RP are both closed set. Now, because this is just for our, this is true because of our definition, okay? Now think about the empty set. Previously, we said the empty set is an open set, okay? And now I see that we're going to say that the open set, or the empty set itself is also a closed set. Why? Because you look at complement. The complement is the whole space, RP. But I know that RP is open. So the complements of the empty set is open. So therefore, the empty set itself is a closed set. The same reason applied to RP. RP previously defined to be open, right? But this here, the RP cell is also closed because the complement of RP is the empty set, which is defined to be open. So RP cell is a closed set. So empty set and RP are two special sets. They are both open and both closed. Okay, besides that, any other set cannot be share the same, carry the same property. Yeah. Other questions? So let me stop sharing. Let me look at the any question. Let me see what if there's open set outside. What is the what if there is open set outside RP? So outside RP, there's empty set. The outside of RP is just empty set. Empty set is closed. It's open, so therefore RP itself is also closed set. Okay. Does C still hold? Yeah. So we also only talk about the open set in RP, and outside RP, that's the empty set, so which is also open. That only set is outside the RP. Okay. Any other questions? Yeah, that is for today. Okay. So I think you need to have some additional time to prepare for the chapter 2 quiz. Okay. All right. Thank you.